In this video, I introduce a continuous relaxation of discrete random variables. Stochastic neural networks with discrete variables are powerful but difficult to train because the backpropagation cannot be applied to non-differentiable layers. The Gumbel-softmax trick approximates samples from a discrete distribution with samples from a continuous distribution. Considering a discrete distribution D, where alpha 1 to alpha n are probabilities, Gumbel-softmax trick for the samples UK from a uniform 0-1 distribution, and then find the key to maximize this term. The sampling of a discrete random variable is refactored into a deterministic function of the parameters log alpha key and fix the distribution. Drawing a variable y with probabilities from alpha 1 to alpha n is represented as a one-hot vector as shown here. The element-wise mean of these vectors is defined as here. The Gumbel 0-1 distribution can be sampled using inverse transform, sampling by drawing U from a uniform distribution and then computing G from this formulation. This Gumbel 0-1 distribution, we sample G key from this distribution. And this 2D simplex of 3 points, y1, y2, and y3 with the probabilities alpha 1, alpha 2, and alpha 3. The derivative of the argmax with respect to alpha is 0 everywhere except at the boundary of state changes, where the argmax is undefined. A continuous relaxation is introduced into a softmax function to define a continuous distribution over the simplex that approximates the argmax function at the samples from the discrete distribution. The Gumbel-softmax trick uses a concrete distribution as the differential approximation of argmax, namely sampling x from a concrete distribution with probabilities alpha as shown here, where tau is a temperature factor and gk sampled from a Gumbel distribution. The concrete computation smoothly approaches the discrete argmax computation as tau tends to 0, while preserving the relative order of the Gumbels, as shown here. When tau approaches to 0, it's a concrete distribution close to the one-hot distribution. And this acceptation of concrete distribution close to categorical distribution. The density of the concrete distribution is computed by using this equation. As the temperature tau approaches to 0, samples from the concrete distribution becomes one-hot and identical to the categorical density P alpha y as shown here. The concrete distribution is smooth for tau larger than 0 and therefore has a well-defined gradient. By replacing categorical samples with concrete samples, the Gumbel-softmax estimator can use the backpropagation to compute gradients during the model training, as shown here. The concrete samples are differentiable, but not identical to samples from the categorical distribution for tau larger than 0. There is a trade-off between small temperatures, where samples are close to one-hot, but the variance of the gradients is large, and large temperatures where samples are smooth, but the variance of the gradients is small. A simulated annealing can be applied to select the optimal temperature. For more details, please check with these references. Thank you. Bye.